All right, thank you. Good. Please, again, do let me know if there's any unstable connection or anything so that you don't miss anything. Today's lecture is going to be about geometry for field theory. This is a topic that's been having recent attention and progress, and I think it is really at the frontier of research at the minute. So much so that I'm going to talk about a paper that I put out today for a bit, not out of the blue, but because it's connected with what we'll be talking about, and you'll hear more about this in SMEF lectures or in the colloquium later this week. But just to repeat some of the takeaways of the last two lectures, let me emphasize these 2 points. We went through the building blocks of the Higgs effective field theory that are summarized here. And in particular, the scalar sector, we chose the composition that it fits heft, and it will also give us the theory at low energies. In particular, we can decouple them in steps. But we have this unitary matrix U that has all of those Goldstone bosons. How many of them? Well, three. The three that we require for the W and the Z. And you can see that there's 3 degrees of freedom, for example, from the constraints of this 2 times 2 matrix being unitary and having determinant 1. That will give you 3. And it has transformed with the polymetrics on the left and the third polymetrics on the right when it comes to hypercharge. And then we have this radial coordinate, if you want, H. I'll avoid using singlet, not to confuse it with other representations. It's a singular representation, as Pyun Wong pointed out last time. That can be confusing, so let's just call it a radial coordinate, or the Higgs particle. This is what we're talking about at the end of the day, particles which feels none of the action of the group. And one of the big questions that we're trying to answer here, and I am disappointed at myself that I failed to emphasize this terrible pun that I wrote in here. This is, given that I'm in England and I'm reading more these days, I chose this wording, to SMEFT or not to SMEFT. That is a question for heft. I said it was terrible, so you are warned. And that question is about when can we introduce that linear representation, that capital H doublet, that fundamental representation of SU2 that is linear and has 4 components arranging all 3 Goldstone bosons and that radial direction in 1 unit. All right. But this lecture is about geometry, how it can be used for heft in particular. And before we go into all the machinery of geometry or any other topic for that matter, I'm going to give you some good reasons to work this theory out. So let's start with why geometry first. It offers insights into a number of subjects in field theory that are a bit obscure otherwise. So intuition that we can borrow from what we know about differential geometry. Some concrete examples are the relation between field reparametrization that we've seen, for example, amplitudes don't care about. If you reparametrize your fields, choose some other field coordinates, as long as they excite the same particle out of the vacuum, and a bit more on that to come. That's connected to a coordinate change. So if you're thinking of, say, general relativity, you do know that it doesn't matter how you choose your coordinates, your charting of space-time, the physics are the same. We'll also sketch, although we don't have time to go into much detail, how correlation functions can be related to tensors in differential geometry, tensors are objects that transform covariantly under coordinate changes, and in turn they will be related in the QFT side to changes of field variables. And there's also a pretty straightforward and useful option of visualize our theories and try and draw them out. So we'll try and do at times. Okay, so that's for why geometry. Now, as to what geometry, how do we pull it out of our theory? Well, for this, let me draw on some of the theories we've written down already. And let's take that Lagrangian for the omega field we wrote some time ago. And let me write it explicitly like this. We have that kinetic term is at the derivative of our omega fields, two of them with two indices contracted with one term was just the identity that I write here at the Kronecker delta, and the other two term was proportional to the omega fields themselves over that denominator. Now, for now, I can just write that as a contraction of those derivatives with a two tensor in field space that I'm calling G with a upper index denoting what coordinates, what fields we're using there. And I'm using that super index not to confuse this G with the G we've introduced before for gauge transformation. Now, to check that this is really a metric, we should see if it transforms covariantly as metrics do. Again, if you can recall from differential geometry of general relativity, all of that would come in handy in here. But let's say now that I know the transformation that takes me from omega coordinates to pi coordinates that we were also using before. Well, if I know that, I just write it out in my fields omega as functions of pi. And then simply the chain rule tells me that the derivative of mu of omega b is the derivative of mu of pi d times partial derivative of omega with respect to pi. Simple as that. And this with the two matrices on both sides, if you want, this partial of the all coordinates with the new coordinates times the all metric gives us the new metric in pi coordinates. And that's indeed tell us that the new metric is the all metric covariantly transformed with these matrices. This can be worked out explicitly. I don't ask you to, but this is therefore a proper metric with these two transformations on the left and on the right. And if we want to draw analogies with the gauge theory that we wrote before, and it'll be good at times because we're talking about covariant objects for the gauge theory and covariant derivatives, and in here there'll be an equivalent of that. So this will be something like that G transformation matrix that we had for gauge theories. And so because this guy has two indices, it picks up to G matrices on each side, so to speak. Okay. And this also tells us, well, I mean, I can use this geometry inside and say what we're doing in here is simply going from one way to parameterize the field space to another one, from a coordinate chart, so to speak, coordinate chart omega to another chart pi. These are just coordinate frames to parameterize the same space, which can be defined without any reference to any specific coordinates, as we've done before, a unitary matrix with determinant 1. And if you write down these equations explicitly, you may realize that these are the same constraints that define a three-sphere. A three-sphere is a sphere in 4 dimensions that you can think of. If x is a vector in 4D, x squared equals 1 will define that sphere. So it's a three-dimensional objects. That's what we call it as 3. And that's what we're talking about here. And that's good because it allows us to take a step back and say, oh, so that's what we're talking about here. When we're using these or those coordinates, it's just different ways to talk about the same physics, the same three-sphere. So let's put this to use in heft. Actually, that was for our series with the Goldstone bosons. It's not much harder to do it for heft. We would also have to take into account gauge transformations to be fully general and connect with the theory of nature out there. So I can just take those, that kinetic term of the Higgs little h that we wrote in there, Higgs particle, and those Goldstone bosons with that function f(h). I'm already writing here that function u as a function of field bar phi over v, so that they're canonically normalized. And these bar phi fields could be those pi fields, could be those omega fields. Point is, we don't have to specify which, because we know what this is just a 3-sphere that we're describing, and it could be described by different charts. So we just write those in here and write this g hat as the metric in a 3-sphere for whatever coordinates we're using. And then that metric that we write in terms of coordinates phi that include both h and bar phi. So let's write that explicitly. Phi I equals h for the first component, phi 1, phi 2, and phi 3. So first the Higgs and the 3 components, and we'll also use this notation in which the index of I, these Latin letters that we use for these 5 fields, run from the Higgs through the 3 Goldstone bosons. And we see that this metric in matrix form is diagonal-ish. The Higgs in our convention is canonically normalized, as it should at the end of the day when you're doing computations. There's no off-diagonal entries because you cannot mix Goldstones with the Higgs and preserve a gauge invariance. And there's this inner metric in here for the sphere with an overall coefficient that depends on the Higgs little h. Now, what we mean by these covariant derivatives of the field phi is explicitly the ordinary derivative, as you have in the covariant gauge derivatives you've seen, times those gauge fields contracted with what we call zeta I, which are Killing vectors. Killing vectors are just a representation of the group in a curved spacetime. They give us the isometries, which is to say those transformations that leave the metric invariant, and the explicit equations look something like this. Derivative of the Killing field with respect to the field phi contracted with the metric twice, and the partial of the metric with respect to phi in the direction of the Killing vector. And this is actually the answer of geometry to the question that we posed a while ago of how do Goldstone bosons transform under this highly nonlinear symmetry transformation. And the answer to that, that infinitesimally this Killing vector gives us, is again in that old notation, the variation of the field phi with respect to gauge transformation G, is those epsilon parameters that we use to parameterize the group element contracted with these Killing vectors, theta I of phi. And then these gauge bosons transform in the very same way that we outlined before with those derivatives of the gauge parameters epsilon and that commutator, something that you can check explicitly. I didn't give you an exercise for this, but I might add it in later. And the key property you need for that, or the thing that you need to realize to see that that is true, is that these Killing vectors present a representation of the group because the derivative of one of these Killing vectors by respect to phi k with index alpha and beta that now run over the generators of your group. This and this Square bracket means anti-symmetric, so alpha beta minus beta alpha. This is again the structure constants for alpha and beta generators, contracted with again for Killing vector gamma. I don't know if it works better for me to zoom in and you to see it, but it does definitely work better for me to write it down. And this, without emphasizing it too much, because we won't be using it all that much, but this is the representation of the gauge group in this curved spacetime, and in general, you can embed it in whatever Killing vectors there are in your manifold of scalar fields. Okay. Now about these covariant objects that we want to build up out of our theory, again, drawing on the analogy of covariant gauge magnitudes, we introduce that covariant derivative, gauge covariant derivative acting on our fields, so that its transformation under the group, it was a simple multiplication by the group element again. We can demand the same thing about geometry and field transformation. So let's take the change of fields and assume that phi is given in terms of another field phi tilde. And we take some invariant that could be the potential, could be something else, v of phi. We can look at the first derivative with respect to the field and see how it transforms. It transforms as simple as given by the chain rule, derivative with respect to phi equals derivative with respect to phi tilde, and then phi tilde with respect to phi. And that's what we want, because that's precisely the same term that enters the transformation of our metric. Now we try and do this twice. Things get a bit trickier. Take two derivatives of that function v. And when you take the second derivative acting on it, after that transformation, you'll pick up a term that hits twice on this tilde field. So the second derivative of phi tilde with respect to the two fields phi. And a term that does indeed transform with two powers of that matrix for each of the indices. So this term we like, but this one here we would like to get rid of. And we do so in, by the introduction of the Christoffel symbol, or the connection that is defined here, as hopefully is familiar to you. But even in terms of derivatives of the metric with respect to your coordinates, in this case fields, and we obtain in this way this field metric, so that in particular we wanted to write the covariant second derivative for function b, and this might come in handy for, but we're running out of letters. Let me call this curve d the second derivative in there. If it acts on b with two indices I and j, this will be second derivative b with respect to phi I by j, but also the connection k ij contracted with derivative of the field. All right, so we'll give us objects that transform covariantly, and we want them for a number of reasons. Eventually, as we've mentioned, amplitudes are invariant. They don't care about these coordinate transformations. So we better keep things that transform in a well-defined manner under those. Right, okay. But I do know that I'm introducing quite a lot of concepts all at once in places that are not all that familiar to you. So it's good to pause and take advantage of some of the easy things to see with geometry that don't require all of these introduction of elements and differential geometry. So let's just think of this arrangement of our three Gaussian boson degrees of freedom with that Higgs singlet. That Higgs radial direction, and think of what could it be. And in particular, is often very useful in physics. What it could be that is the nicest And by nicest, we mean the most symmetric cases that we could have for this manifold. So if I were there, I'll stop here for a second and ask you to think about it. What is the most symmetric four-dimensional manifolds? Instead, I am talking a bit longer so that you have time to think about it. And now I'm going to write it down for you guys to see. Something that you might not know is that these most symmetric four-dimensional spaces have a common property, and that's all of them have constant curvature. So the curvature is the same at every point in the manifold, which is perhaps not so hard to believe if you're looking for the most symmetric cases, because in that case, any point is like any other point in your manifold. But now just to lay them out explicitly in terms of that curvature, you have constant curvature, let me call this R, which is positive. At every point, you get a force here. So that is just the extension to 4 dimensions over the 3 sphere that we had in there, with the Higgs degree of freedom extending it to a 4 sphere. Or you could have the curvature is exactly 0 everywhere. Looks like a special point, and is R4. Indeed. Or you could have the other sign for the curvature, and that will give us a hyperbolic space, which is somewhat related, we'll see now, to something like Minkowski space in a sense. But these are the possibilities that we can just list with a little thinking about geometry and what will be those cases. And what's more about each of these cases that do correspond to theories that we're familiar with. Well, for one, this flat case will be none other than the standard model. In that case, curvature is 0, and as we'll see, that also means that all of the unitary problems go away. This case in here is actually related to minimal composite Higgs models, for a reason that I'll make explicit just now. And this other case, well, we don't quite know what it is, but it seems, at least for the low energy point of view, to be on the same footing as the other ones. So let me be slightly more explicit on this and actually draw it, because here you go. Nice, everybody loves pictures. This is an attempt at drawing this in 2 dimensions. So reducing all of 4 dimensions to 2, because we cannot quite do it in 4 dimensions. And here we have this vertical axis around which in this reduced space gauge, the gauge action will be just to rotate it in that direction. And then that radial direction will correspond to O little h. So you can see here that 4 sphere will look like a 2 sphere. The standard model will be like a plane. I'm just cutting it at the finite radius, but this would extend. And that hyperbolic space is hard to depict because it has one of the metric is not positive definite, but here's an attempt at it. The reason why this S4 case is a minimal composite Higgs model is because, as you can convince yourself, or perhaps look up in math books, the breaking of SO5 to SO4, which yields 4 Goldstone bosons, it also yields this coset manifold is isomorphic to S4. That's a plausibility. I haven't made it more explicit, and I won't have time to, but you can, for example, in one of the exercises that I suggest, you can take this breaking pattern, use our CCWC procedure that we outlined for this we are aligning for any group, so we can use it for these groups in particular, and obtain the metric in this 4D space that will correspond to that in terms of sines and cosines. And I do encourage you to do it. It's outlined in the notes. In that sense, this hyperbolic case will come from the breaking up. So 1, 4 to SO4. While the analogy there is simple to draw, the construction of UV models is more challenging because this 1, 2 means that one of the entries in our metric is negative, and that will lead in general to ghosts in our theory, so it's hard to build an ultraviolet completion of this other case. Okay, good. So after this visualizing break, let's go back to a bit more equations, but hopefully this is something familiar. We're just writing the Riemann tensor now, but for field space, which is where we live now. Explicitly, the Riemann tensor with its 4 indices will read like the derivative of the connection with respect to the field. The connection square with this index m summed over, repeated indices are summed over in this notation, and symmetrized in the last 2 indices. Again, we're using this notation in our case, in which I or Latin lowercase indices run from h to 1, 2, 3, that will sometimes denote with A, B, C to make it different. And if we do this computation, again, I outlined, well, I mean, you probably computed a Riemann tensor before, and you can even perhaps recycle that computation if you did it for cosmology. What we have in here doesn't look all that different, with our function f being something like that scaling factor in cosmology. So you can even recycle those results. But with the inner metric now being a 3-sphere, it will look like a closed universe. And what you do if you compute this explicitly for that metric, you will see that all but the elements with 2 Higgs insertions and 2 Goldstone insertions vanish, or 4 Goldstone insertions. The first case is proportional to that inner metric over x squared and a function r of h. And the other one is proportional to another function with an inner metric in there. These functions look like r sub h, like the second derivative of f over f itself, or r of phi 1 over v squared x squared minus the logarithmic derivative of f squared. And I don't know if this rings a bell for you guys, but we've sort of seen this before, taking into account that our normalization is that f of 0 equals 1 to keep v the electroweak BeV of 246 g-electron We've already written down the amplitude for WW longitudinal scattering as 1 over v squared minus f prime squared times the center mass energy. And this one you've done yourselves, but we have also sketched how the amplitude for WW to Higgs would be proportional to f prime times s minus, actually. But these guys are just these other guys if I substitute in f of 0 equals 1, so evaluated around the vacuum, which would be something useful to note, but it actually goes deeper, and as we'll see in a minute, and this is no coincidence, but a consequence of geometric analysis of our amplitudes. Okay, so hopefully I can spark your interest, and we can now go a bit more into detail as to how geometry and amplitudes are related. And for that, we'll look at the LSC reduction formula. This really captures on its name, actually. It's a reduction formula. It gets rid of a lot of redundancies in the Lagrangian description, and it gives us the S metric and amplitudes within it as a result. For that formula to work, or to give us the same amplitudes, there's just this requirement. So this is valid for any field variables that you choose, but there is one thing we should demand, and is that in this possible field transformation from variables phi to variables phi tilde, we should have, if I'm giving it indices, then let's give it indices, that there's a series expansion of this transformation, and it starts at the linear level. And then you can have however many powers on top of that, but no constant term in there if you want the two fields to create the same particle or excite the same particle around the vacuum, which is to say, if you sandwich this field phi between a particle state and the vacuum, you get a non-vanishing matrix element, and you will also get a non-vanishing matrix element for the same contraction with phi tilde. So provided that is the case, we don't even care, the LSC reduction formula doesn't even care if you have an overall constant C. You will get rid of all of those, all of that normalization redundance to give you the actual amplitude at the end of the day. And we've encountered explicit cases of this already, and this actually can shed a little light on some other discussions we've had in these lectures. For example, we do know, we've seen that pi and omega variables give the same amplitudes, and they are indeed just two different ways to parameterize that sphere. But furthermore, they're variables that when we expand, or when we see how this chart maps into the sphere, and we look at the vacuum, let's say it's this point here, these two parameterizations on these variables, this is changing one of the pi's while keeping the other one constant, and you obtain this by changing some other of the pi's. They are related linearly by that term in there, which means that in a neighborhood around the vacuum, they do point in the same directions. So really close to the origin, these parametrizations are the same at that linear level, but they differ when you get further away. They will parameterize the manifold in different ways, but at least around the origin, they're pointing in the same direction. That tangent space for each of those Goldstone coordinates is the same. It applies to Higgs effective theory, and this discussion that we had of, well, why are you calling this little h the radial coordinate, whereas some other people, if you have, for example, the standard model that we're assuming here, will write it as a doublet, and we'll say all of those amplitudes you're computing are actually for this real component of the lower entry of our Higgs doublet. So it's all of this discussion of little h of what we call here h0, that real part just talk, does it matter much? And at the level of the amplitudes, the LSC reduction formula, it tells us that it doesn't matter. They will both give us the same type of amplitudes, whether you have this or that one, although I mean, for the Lagrangian and UV purposes, it does matter, don't get me wrong. But if we just look at the LSC reduction formula, we will get that this definition tells us the real part of the Higgs doublet, which is to say the BEV plus H0, is just the real part of the second entry of my unitary matrix times V plus H in that notation. But if I write this a bit more explicitly, I will get V plus H0 equals, remember that we expanded around U equals the identity, so this is going to have a 1 plus the next order will be order phi squared over V squared. And that would allow us to cancel out that V term to first order and do relate H0 and H. They're not exactly the same, but around the vacuum, they point in the same direction. And we can do a little better than that. We can try and draw it. So let's zoom in here now. So these green are again coordinates for our little h and phi coordinates, which is in this reduction to two-dimension manifold of our Higgs tablet, radial and angular coordinates. And again, in this space, H transformations act rotation around the origin. But we don't expand around the origin, we expand around a finite f away from that origin, somewhere in here. And for that space, the coordinates that we've chosen around that point is our angle will be this phi in here. Our eta coordinate, this imaginary term that we have in here, will be something like the y coordinate. So we're pointing in here, is this direction here. While the radial coordinate will be this little h in here that happens to be pointing in this point, in this spot, as the same direction as h0. And this guarantees that whether we're using that in the standard model, whether we're using that linear realization and computing scattering matrix elements for eta, that imaginary part will be the same as computing it for the Goldstone bosons, and that little h will be the same as that real part of the doublet. Okay, hopefully this has cleared up a bit some of that discussion, and it should also be remarked that I'm discussing this for the standard model case. It'll be somewhat analogous in this method, but again, one of the big questions in heft is whether this equation can be written at all or not. So it may not be written, and this discussion wouldn't go the same. But now for the actual LHC reduction formula, provided this is the case and our field excites the same particle out of the vacuum, we can write the S matrix as the product of poles or kinematic variables for each of the particles involved in the scattering over the square root of the normalization. We'll see how we define that in a minute, of correlation functions, whether you like to define them with the path integral formalism, taking variations of the path integral with respect to the source J momentum representation, or whether you like it to write it as this correlator of fields evaluated in the vacuum. What the LHC reduction formula is that all of those redundancies and we're getting rid of, because we're multiplying by all of these inverse propagators in some sense, to take the residue of our correlation functions on shell, because we're taking these on shell, and only those residues on shell survive to give us the S matrix element. In the process, we get rid of a whole lot of junk that doesn't enter the S matrix, and in all of that piece of the correlation function that we're getting rid of, there's all of those redundancies that won't enter the results, and the reason at the end of the day why you computed two amplitudes and you got the same result. Okay, now we're talking about geometry, so we would like to have an understanding of this formula for general manifold being our scalar assemble. How do we go about generalizing this? Well, let me note how this set normalization is defined to try and draw an analogy with geometry. The two-point correlator is proportional in this normalization to that factor of set in the numerator. That's the way you can define it if you like. And that would come, if you look at it, it's set over p squared over m squared. That would come from a Lagrangian, will look something like the kinetic term, something like the inverse of that you've seen in there. The second derivative acting that phi and that other phi minus m squared with that normalization set. Now, if we just draw a naive analogy with geometry and what we were doing there, we'll have that this is something like, let's have it be massless for simplicity, or derivative of a field contracted with the metric evaluated around the vacuum, whatever that is. Whoops, what happened? Okay. Sorry, this. There we go. Contracted with the metric evaluated around the vacuum and two derivatives of our field. Called the G phi to keep with that notation. And then the analogy is sort of clear. 1 over z will be equivalent to our metric. But what shows up in the LSE reduction formula is the square root of 1 over z. So how can we make sense of that in terms of the metric? Well, hopefully you're familiar with the Irvine. I'm not sure I'm pronouncing that right, but we can define the metric as a product of two tetrads or Irvine that take us from flat to curved space, maybe using this in general relativity. So that what we have now as 1 over the square root, this analogy of z will be that Irvine. I'm calling it E, but please don't mistake this for the number E, 2.712. This is just an object with two indices that takes us from curved space to flat space. That will take into account that normalization term. Then we also have to take into account what these correlation functions look like in a curved spacetime, in a full general manifold. And for that, let me just note that these guys have indices A1 through AN, with our notation of, with the metric, remember, has ij sub-indices, and then these guys have upper indices. So this will be like the generalization of this will be therefore a tensor or an object that has these covariant transformation properties with n upper indices. For that, we have to choose Riemann normal coordinates. I don't want to go much into the details of this, but the fields themselves don't transform covariantly. We can instead choose coordinates associated with geodesics that pass through that vacuum, through that origin, and those will transform covariantly. For the time being, let me just assume that that correlation function is covariant and write the formula of the geometry. Let's see. That will be the product of pi squared mi squared 1 over square root of z. That will give us the Irvine A1, or A sub I, where I runs from 1 to n. Some of these particles will be incoming, some of them will be outgoing. So the correlation function of phi hat will be the Riemann normal coordinate A1 to phi hat AN. As simple as that. This is a formula that's been, I guess, implicit in my mind for some time, but I never spelled it out. And I think it's interesting to remark that it was these lectures that made me write it down explicitly. And I was about to put out this paper with my student, Mia West, and this was just related to what we're putting out. It's out in the archive today. It has to do with loop computations to any order in a curved manifold, and we put it out in there as well. To my knowledge, I haven't seen this anywhere else. So I think it's genuinely new, and knock on wood that is true. I don't know, maybe it's in some Russian obscure article in the 70s. But this captures for what we care about in this lecture is that geometrized version of the LHC reduction formula. Not only that, but there's an exercise in the notes for you to try this explicitly by recycling what we wrote as the amplitude for WW scattering. If this formula is anything like correct, then what we were writing in there, those amplitudes that were proportional to curvature elements are indeed written explicitly as the center of mass energy times Riemann tensor upper indices that will come from that correlation function contracted with Vierwein's. And in particular, the W plus or minus selects the first two Goldstone components in a combination of those. So it will be 1, 2, 1, 2. And then you can compute the Vierwein that will come from that. The metric that we're using will be something like the square root of S squared. So we'll have that factor of F in there. And this will tell us that it looks something like F to the 4th times that upper index Riemann tensor, and that gives us precisely a cancellation of F's and the amplitude as you know it. But this is sort of trivially true because we have in our convention that F of 0 equals 1, and that's where we're evaluating it. What we can do, and the exercise that I actually suggest you do in the notes, is instead revisit our amplitudes where the bev of the Higgs little h is not at 0, but at some other point, h star. And we can check this relation because we can compute independently both sides, so to speak. Well, not so to speak, literally. You do know how to compute amplitudes on their own. So we can sort of look at the left-hand side of LSC. We just revisit our Lagrangian. Now we will expand around this h star point. So the first term in the expansion of that Higgs around the new vacuum will be just F evaluated at h star squared times the matrix of Goldstones. But now note that the normalization of these fields omega, or if you want to choose pi, you can do that as well. It's not V, the electroweak bev, but it's on V star. Different because the coefficient of this prefactor of the Goldstone boson term is different, and we can find the relation between V star and V and H. So V star as a function of V and F of H star is given by canonically normalizing. It's not too hard to get once you expand that Goldstone matrix and look at the first term in the expansion, the kinetic term, and you'll find that relation. And then you can put it, substitute it back in the linear coupling to the Higgs, and also this was that quartic Goldstone boson coupling. And you can then recycle the computation for longitudinal scattering that you already had, or we're changing after all these those coefficients of Fame and rules. You can assemble them together just as well and find the left-hand side. And on the right-hand side, you can just evaluate this formula again. Instead of around F0, you can around H equals 0, excuse me, around H equals H star. And that same cancellation of F's will occur. I will get, again, that expression. Good. So I think this actually does clear up some of the questions in the at least I had about what is the explicit relation of these amplitudes and curvature elements. Why is it that those terms in particular show up in there? And at least personally, it's really nice to see it explicit. Now, excuse me. Let's put this geometry to use and see what it can tell us about the SMEPT versus the hep question. And this is another exercise that one can do. You can write down, as we do in here, the linear representation and the SMEPT with a couple of operators that will contribute to those kinetic terms. So we have here just the simple kinetic term for the Higgs, as you would have it in standard model, but with the addition of two operators denoted with, maybe, I'm not sure if Professor Trotter is using the same convention, but it's self-contained within the discussion. The derivative of h dagger h, this can be an ordinary derivative because it's an invariant squared, or that kinetic term with an extra factor of h dagger h. And we can try and equate this to the form that we have in hep and try to deduce if there's anything special about this SMEPT case that we can pin down when comparing with hep. You may think, well, we just wrote amplitudes in terms of these two elements of the curvature, r phi and rh. So maybe there's not no prediction because we also have two operators in here. But you can actually do the exercise explicitly in a number of ways and realize that it's only one physical parameter entering at the end of the day. You could use the equations of motion, or what I suggest one can do in the notes is use geometry instead. That will be something like a change of coordinate. So we can again use this rewriting of the Higgs doublet in terms of a radial coordinate and some bev that is not exactly 246. And then write this left-hand side of the equation in terms of those guys as kinetic term for this h underline with some function of h itself out front, and then some other function of h in front of the kinetic term of the Goldstones that I just condensed in that expression there. Compare with the kinetic term that we write for hep and realize what is a change of coordinates h underline 2h that will take me between the two frames, just as you would think about in geometry. The derivative of this transformation h underline with respect to h, you can deduce yourself that will be something like 1 over square root of k, and then you can use that expression and the chain rule to rewrite those curvature entries that we wrote in terms of derivatives of f with respect to h as derivatives with respect to h underline of these functions that show up in there. Then expanding to 1 over lambda square, because we're only considering SMEPT to that level, expanding to 1 over lambda square everywhere and only retaining those corrections, you realize that the two curvatures are actually correlated and the same and given in terms of this combination of those coefficients of the operator, which is great for phenomenological reasons, because you say, well, there's a clear prediction of SMEPT, that it need not be satisfying heft. In heft, you can have these curvatures be whatever, pointing in whatever direction. So this gives us hope that we can actually pin down when we have SMEPT or heft. In fact, you can be so emboldened as to try and go beyond the leading order in SMEPT and try to generalize and say, well, maybe I can always use this to tell them apart. It will be great and experimentally very definite. But when you try and do that, you can be general and write instead of constant coefficients. If you like, you write functions of h dagger h in front of each of those two guys and try and do the same exercise in general. Well, what one does find is that the correlation is lost at dimension 8 when you go one more order from these leading corrections in SMEPT. So this is not quite it. We cannot generalize this to any case, and in particular to subleading corrections. So there must be, or we hope there would be, a better way to tell the two apart. But that is the subject for the next lecture. And I think just as well, because I've been talking for about an hour now, and you might have questions that I'm happy to take now.
Okay, let's thank Rodrigo. Questions from the audience? We have one.
Thank you. So I have two questions, and so let me ask the first order. So firstly, when I see that we're defining the metric between the field so that we can measure the size of the field somehow, and when we are like relating the endpoint correlation function and the endpoint, which is defined as the field space manifold, it seems like to me that we're dealing field as some kind of tangent vector on the field space manifold. But if that is the case, then there needs to be a point about which we are defining the tangent space, right? So is that point the ground state in some sense?
Right. So there's where could this be seen clearer? Yeah, so for example, this right here, for the LHC reduction formula, we're implicitly assuming that we're expanding these fields around the ground state of the theory, so that they truly excite particles, because after all, what we call particles for the point of view of fields are just excitations over the ground state. So I'm assuming that that these fields are truly in our manifold parameterizing deviations from the vacuum state. Wherever the vacuum sits at is something that I'm sort of assuming that's the, well, I mean, for a theory to kind of make sense, that's where we're expanding around the vacuum, at least for right, well, in the vacuum state, you could have things be different if you're looking at thermal field theory or other cases, but we're thinking about scattering and the LHC and these experiments, we are implicitly assuming that the fields we're expanding around are truly deviations from the vacuum point in the manifold and excite particles. That is why, and this I'll talk about this in the next lecture, but it's also one of the reasons why doing SMEFT is in some sense a bit more complicated than doing hep, because in hep, sort of by assumption, this little h is parameterizing deviations from the vacuum state. But when we write that h field in hep, we call h dagger h is v star halves, or let me write it like this, v star plus h square root of 2 squared. And the implicit expansion in SMEFT is on powers of, among other fields, h over lambda. I think I'm saying too much about the next lecture, but anyway, let me stop here. On powers of this guy. So that assumes like a Taylor series around H0, but in reality, that's not quite the true vacuum because H takes a bet, and we really have to introduce this other field, which is the true Higgs field that excites particles out of the vacuum.
Okay, thank you.
Okay, thanks.
So, yes, and can I ask a second question that I have? So, okay, so the second question is more about the purpose of doing the field theory in this way. So probably you might have mentioned this at the beginning of this whole lecture series, but probably then I just missed it. But still, because I had it. So is the purpose is about like attempt to get full covariant expression for endpoint correlation functions based on some calculation over some certain like field parameterization, which particularly make the calculation easier?
Mm-hmm. Right, so I think well, I don't think I've mentioned how that is done explicitly. So to get, I think some of these issues people in string theory might have dealt with before, but just having trouble translated what string theory people do and low energy physics. But when I'm saying that I'm trying to generalize correlation functions in particular, which are just insertions of our field over the vacuum to things that will transform covariantly, which is to say they will pick up factors of phi over phi tilde for each of the terms, so that at the end of the day we can build invariant objects with this. The field itself, when we write a transformation, something like this, that's itself, I mean, this is not a proper transformation property, it's just an equation that we write for the change of coordinates. But if we introduce Riemann normal coordinates, as is done at times in string theory, one can define geodesics that goes, again, the vacuum is whatever point in your manifold, but it's somewhere here. And where my coordinates that parameterizing deviations around the vacuum in whatever two directions, I can always define the geodesic that goes around the vacuum with that same tangent in any of the one directions I'm writing about. But that is a geodesic, and we defined our new Riemann normal coordinates. I'm using eta in my notation as the derivative of phi with respect to sigma evaluated around the vacuum times sigma, where sigma is the length along this geodesic. So eta equals 0, that's correspond to phi equals 0. And it is in terms of these Riemann normal coordinates that we guaranteed to get objects that transform covariantly. So now this would check for correlation functions. And in particular, just let me just say this one more thing and I'll let you go because I know it's late there. The expression for the S matrix that we had, in top of those correlation functions has these Beer-Vines. So for example, EAI and EJ for these two elements. And one can see that because these are lower indices we contracted it with, the full expression for the S matrix will have those terms transforming from the correlation function, but also from the Beer-Vines will have the opposite or the inverse matrix to cancel those out, so that at the end of the day, that expression for the S matrix does not care about these field definitions. Was that, sorry, I think the sound was a bit unstable, but I thought that was what your question was about. Is it?
Yeah, I think it's been answered. Thank you.
Thank you.
Any further questions?
Thank you for the nice lecture. I also have two questions. And so you also have the complete form of the higher point scheduling amplitude, and it also have some kind of, I mean, we can see the kind of the cutting rule or something from that.
So you said higher form?
Higher point. I mean,
Oh, yeah.
For example, 5 point, 6 point.
True. Yeah. So this is, well, that's what I was trying to write implicitly in those equations. You can have these as many A's indices as you want, from 1 to AN, and then you'll have to insert just as many Beer-Vines in here. So there's just one tetrad, one Beervine for each of the fields insertions, and you can get out of the endpoint correlation function, you can get the S matrix element with n total particles, some of them coming in, some of them going out with this expression. So that's
So my question is, with the kind of Riemann tensor or something?
the question is how we define the Riemann tensor?
No. I mean, endpoint correlation function is also can be written with the Riemann tensor and Beervine.
I think if you're asking about why does it happen that in this case we get the Riemann tensor in is okay. That doesn't generalize. You're right. This is so the Riemann tensor is a candidate to be in our amplitude because it does transform covariantly. So if it's a profile, but not up until you do make computations in your theory, you find what are the tensors that enter the eventual computation. So that's a very good point to raise. It happens to be the Riemann tensor in this case, but it could be any other tensor construction in other cases. And in particular, if you go to higher endpoints, you'll have tensors with more indices. For example, one can see that one can compute one loop elements from that leading order Lagrangian and get that some of the terms in your action depend on the Riemann tensor squared. So I would suspect that, for example, a 8-point interaction will be given in terms of 2 insertions of the Riemann tensor or other constructions that one can do. For example, I think in my notes, there's more references, but we've seen and people have computed higher Gauss-Thompson scatterings. Again, these are not the most generals, but for example, W to n numbers of Higgses. So this could be 2 to 2, but also 2 to 3, 2 to 4, 2 to 5. And these ones are given in terms of covariant derivatives of the Riemann tensor. So you can take a covariant derivative as many times as you want, M, and obtain an object that has every time one more index. So this actually has been generalized to this type of, well, those expressions are known, and they're in this paper by Cohen, Craig, and Lu. It's referenced in the notes, and that's how they look in particular. But in general, they have to be tensor. They don't have to be either the Riemann tensor or its derivatives. But for this sector of the theory, it happens to be that these are the ones that show up.
Okay, thank you. And my second question is, this formalism can also cover the interaction which don't have the derivatives.
Mm-hmm. Yeah. So that will be very much related to what we talked about here. So for example, the potential, in here we just computed something that would be, again, a tensor now built out of 2 derivatives. There's so many derivatives, it's hard to keep up, but these are derivatives with respect to the field. So they don't have powers of momentum, space-time momentum in them. But you can derive from this will give us this second derivative with respect to fields of the potential will be related to masses, of our particles when evaluated around the vacuum. It will appear in particular in the propagator, but you can also define the third derivative, again, with respect to this field of the potential. This will give us something like a 3-point function, and you can build amplitudes with these vertices as well. So it does also apply to these type of vertices without space-time derivatives. And actually, there's quite a number of equations in the paper we put out today with this type of term. Sorry, I don't know. Is that what you asked about, or you got?
Sorry, I really confusing it. I mean, your the tensor for field metric is only for kind of
So this is
sorry, never mind. Let me think by myself.
right. Well, let me just say, in case that derivative argument is not all that convincing, that you can equivalently obtain a covariant expansion if you find the explicit change of coordinates from eta, or the other way around, rather, from phi to these eta coordinates. If you find this change of coordinates from ordinary coordinates, if you like, to Riemann normal coordinates, giving us these geodesics, a simple expansion around eta is guaranteed to give you a covariant expansion. That, I mean, when you do it explicitly, and again, this is outlined in a number of papers, you see that that expansion in eta will give you covariant derivatives as we've defined them earlier when acting on the fields. Again, I'm sorry for the ambiguity. Covariant meaning derivatives with respect to the field. That was supplemented by that connection.
Okay, any final questions? If not, let's thank Rodrigo again.
Thank you.
Any announcements? No? Okay, well then we'll meet back tomorrow.